So let's start. Good morning, good afternoon, depending on where you are. This is Aminul Haq from EPRI. Welcome you back to our second day of the Inverter Fundamentals and Grid Support Technologies tutorials. In this morning session, we'll be discussing the actual grid support functions that we normally known as the smart inverter functions. So I'll give the examples of what does that function means and also show you results either from the laboratory test or from the field demonstration. So again, thank you all for joining again. Let's start. So as we mentioned before, we are recording this webinar so that can access that later. And as I mentioned in the previous day, just to remind you, the materials are available in this member center. And they're also available in the box folder that we created and shared the link before in the prior day. So either way, you can find get the materials depending on what your IT allows you to connect. Some cannot access box, so for them, the member center is a better option. And you can clearly see Amy already created a folder there, November 2020, and the materials are available, available there. So this is the latest one. You can also find the old ones. Did anybody try to get the materials from the member center?
It's not related. I can't put that in the request.
Okay, it's hearing some background discussion. I will remind you to mute yourself. You are not participating. But at the same time, I would suggest that you check whether you can unmute yourself, because you should be able to unmute yourself and participate, but we don't want to have a situation that you cannot unmute and ask questions. So if you have any problem unmuting yourself, you can either raise hand or send a message to the chat, and Amy will try to fix that. Okay, with that, let's get into the main topic. So today's discussion, as I mentioned, we'll be jumping into the main grid support functions. We'll try to finish it. If we run out of time, we may still take the break at 1 or 1 minutes past the hour, and then try to recover that in the afternoon session. So we'll do 11 to 1, maybe a couple of minutes past the hour. Then we'll take a break and then come back at 2 o'clock and wrap up the tutorial with some interconnection standard discussion, like 1547, what are the main changes. We'll also talk about the UL certification. So that will be the afternoon session. So quick summary. We discussed these topics last sessions on Tuesday. That inverter, if you take an example of a PV inverter, it converts the DC power generated by the panels into AC power, and that goes to the grid. So basically, inverter is the interface between the DC generation and the grid side AC power. So that's why most of the critical functionalities like matching the voltage and frequency is the responsibility of the inverter. Unintentional islanding protection is a expected function or behavior or capability of inverter. We discussed harmonic, that prevention of high harmonic component injection is also part of the job. Ensuring maximum power point, that's a requirement. So inverters are doing all these things from the beginning, like whenever the first standard was published, or even when first inverter was produced, maybe back in 90s and 1900s. Still, the inverter were not called a smart inverter at that time. So the question is, what makes the inverter smart? So this is the definition that I'm using for a couple of years, not necessarily across the industry is a standard, but this is a way I explained, and so far didn't hear a lot of opposition to that. So the way I see it, that inverters that can modify its real and reactive power output. So inverter can modify without any external entity its real and reactive power output to provide some sort of grid support, and can respond autonomously to voltage and frequency changes. So inverters see a change in the voltage or frequency at its terminal, and based on whatever way it is programmed, it will respond to that by changing real and reactive power. So that's autonomous. The other option is that it will simply respond to an external command, like a DMS or DARMS or plant controller is sending a command. Inverter will respond to that. So that's another option. So one way is that inverter responds autonomously based on voltage frequency and based on the characteristics curve. We'll show a couple of them today, and it will respond autonomously. The other option is that it doesn't do any calculation. It just responds to some external entity like plant controller, DARMS, and then respond to that. So that's how I define the smart inverter. If we think about, or if you do the analogy of the old Nokia cell phone back in 1990s, its job was to do audio conversation, so mainly making phone calls, communicate with people. If you see into the new, nowadays, the smartphone, its basic function is still remain the same, at least if you ask for the new generation, that audio communication. But what happens to the smartphone is that now it has tons of other capabilities in addition to the making a phone call. All these apps, now you can watch movie, you can pay for your coffee. So a lot of things you can do with a smartphone, which was added on top of the fundamental job. So that's how I see the inverters also. Its fundamental job is still the same, convert the DC into AC, match the voltage and frequency. But in addition, now it can provide reactive power support, frequency watch support, write-through capability. So those are the additional features or functionalities are added to the inverter, and it was able to do it because of its power electronics, all the DSP microprocessor-based control available inside the inverter. So that's kind of the way I see that inverters has evolved, but its fundamental job did not change, but new functionalities and features are being added. And accordingly, the standards are also getting up to date, adding more and more guidance or requirements regarding what the inverter or new inverters should or DES should do to support the grid. So that's the kind of evolution happening. The other way to see what the inverters can do, smart inverters can do, a lot of its functionalities are related to voltage management or help to regulate voltage or manage voltage. So those are mostly distribution-oriented functions, or distribution operators are mostly interested on those functions like fixed power factor, volt var, volt watt. Those are all related to the voltage regulation. There are other group of functions which are more like a load and generation balancing or bigger area power system frequency-related function. So voltage right-through, frequency right-through, basically fault right-through we're talking about here. Similarly, frequency watt, active power injection or limiting active power injection, basically where you control the amount of power generated by the plant or injected by the plant. So those are ultimately in the bigger scale, it's a load and generation balancing related functionalities. So which are more transmission operators are more interested in those functions. So, but DR can provide both. Depending on where they're located, requirements might be different, but the capabilities are available. And inverters are not typically designed for either distribution or transmission. Inverters are designed for inverters. When it is being applied, some requirements might be more important than the others, depending on where they are connected as a plant level or system level. Other part where you're saying that more and more is the configuration, coordination, real-time feedback. Those are very important for management of multiple resources, like a large number of a large fleet of distributed resources. If you want to manage them, you need coordination, you need real-time feedback, monitoring system, and control system. So communication and interactivity or interoperability is very important there. So that's another way to see what these smart inverters can do, and depending on which area. Any question, comment? Okay, next, the way I organize them, we'll talk about the voltage regulation support functions first, related to voltage. Then we'll go into the load and generation balancing or transmission related functions. So if you check all these standards or different products, these are the voltage-related functions are discussed or available in the market or in the products or in the standards. Not necessarily every standard has everything, but these are known functions basically. And you can see that most of them are reactive power-based functions, like the top 5 mentioned here. Those are all some sort of reactive power control. In terms of active power control for voltage, so far I know of only one function known as volt watt. So that's how you can think about that. Most of them are reactive power, like they are controlling the reactive power to help regulate voltage. And there is one function which is actually controlling active power, which is volt watt. So among these functions, the most common ones from the reactive power side is the fixed power factor and volt var. So number 1 and number 2 are the common, most widely used or commonly used reactive power-based functions. Volt watt function is also available in most commercial products, but its utilization is not that wide like the power factor or volt var, but people are gradually starting to understand its importance. So we'll mainly discuss those three, and the other ones, we may discuss some of them during the IEEE standard discussion in the afternoon. So the reason I showed that again, cell phone picture on the right, if you check your cell phone, most probably almost all of you have more than 2 navigation type of apps in your smartphone, from iPhone 1, Google One, you might have Wedge. So a lot of people have multiple navigation tools. But any given time, if you want to use the navigation, as a user, you have to select which app you want to use. That's number 1, that you're selecting which app. Number 2, you have to say where you want to go. Once you select the app, once you put the direction, after that the app becomes smart and then gives you the direction, reroute if you change the direction. So similar thing for the smart inverter. The inverter does not know which function to activate. As a utility, you have to specify that which function you want the DER to activate, power factor function or volt var function, whether volt watt function should be active or inactive. As a utility, you have to make that decision, number 1, so which is like selecting the app. The second part is that once you select the power factor, you have to say which power factor you want the inverter or the plant to operate at. Is it unity, or is it 0.98, is it 0.95, is it absorbing or is it injecting? So you have to provide the settings. Not only just you select the app, you also have to give the direction. Similarly, you select the function and then you have to provide the settings. Same thing for volt var. If you select the volt var, you have to provide the volt var curve or characteristics curve that the inverter will follow after that. Once you activate and provide the curve, after that, changing the reactive power based on the voltage is autonomous. So that part is the smart, but not knowing which function to use, that is not that smart. So as a utility, you have a lot of responsibility to select the function and select the settings. So we'll start with the power factor, the simplest one and being used for several years now. So very simple is starting point, and just to remind, unless the utility asks for any specific function to be active, the default will be always a unity power factor operation, the way it is being done for last 10, 15, 20 years. So again, if you don't ask for any specific advanced functions or non-unity power factor setting, the default will be the unity power factor the way right now I'm showing in this picture, as if it's a kind of early morning, the plant is generating 40% of the nameplate power, and you can clearly see reactive power is 0. If the sun goes up, power will go up, but it still remain on the unity power factor line. If the cloud comes, it will go back. So power will always change depending on the solar condition, but it will stay on the unity power factor line and reactive power will be 0. So that's the unity power factor operation, very simple. Now, if you ask for a non-unity power factor, 0.95, 0.96, whatever it is, some non-unity power factor, and I'm showing an example. In that case, the operating line is not on the unity power factor line. This is the operating line depending on the power factor, cos theta. So this is what is happening now. This is the corresponding power, which is dictated by the DC power or solar condition. And because you ask it to operate at a certain power factor, it will have a corresponding Q value to maintain that power factor line. Now, at this condition, if nothing changes, it will stay there. Now, if the sun changes, sun goes up, irradiance increases, power will go up. So power is increasing. But the inverter, this is the autonomous part. So once the power goes up, it knows that it has to maintain the power factor of, say, X, 0.97. So that means since power has gone up, reactive power also has to go up. So it will automatically increase the reactive power to maintain the power factor until it hits the circle. So this S is the limit. This is the VA limit. So it will continuously do this as long as it's within the circle. So this is what is important, and we'll discuss that again later. So this part is autonomous, that once you specify the power factor, basically you're specifying this line, then depending on the power, reactive power will change because of this solar irradiance, but the inverter will correspondingly change the Q to maintain the power factor. So that's the fixed power factor operation. Once it gets to a situation where if maintain the power and Q will push the operating point outside the circle, that time it will limit either P or Q. So if it's a position that power has gone here, which will corresponding Q point will be here, it will never go there because it cannot operate outside the circle. In that case, either it will limit the Q and stop here, or it will limit the power and go to the Q value of something like this. So that will depend on this reactive power priority or real power priority. Any question or comment on that topic? We'll discuss that again with another example. But so this is the simple power factor operation. Similarly, you can go lagging, leading, whichever direction you want to go. There is one thing I highlight that I intentionally did not use plus minus or leading lagging, because there is a huge confusion in the industry that what sign means what. And as a power engineer, you may indicate something. On the other hand, the technicians that go to fix the inverter, they may interpret it different ways. So it's always a good idea to clearly say it's injection or absorption. So typically injection means like behaving like a capacitor, increasing the voltage. Absorption is like behaving like inductor, pulling the voltage down. So that's that way, at least I like to explain it that way. I'm not sure there's a comment. Let me check. Okay, so there might be some question in the chat. For Q injection, are you referring to DR injecting back to the system? Yes. So here by injection, we are referring to that DR plant or inverter is injecting VAR to the system like capacitor, and normally that will push the voltage high. But most cases, since solar backfeed cause over voltage, your expected behavior is that the plant will absorb VAR to pull the voltage down or keep the voltage low. What are the challenge related fixed power factor in the DR industry when P megawatt is very low? I will show that example later. If by challenge you mean that maintaining a fixed power factor, I have a very good example results for that. We'll discuss that maybe 2-3 slides later. Okay, so let's move on. I like to show you a real example from the field, and you can see the date is back in 2012. So that's what I meant, that power factor function is being used for a long time. So this is a 1.8 megawatt plant in Northeast, kind of an agricultural farm. And these dots represent a 10-second average voltage measured at the low side of the transformer, interconnection transformer. And x-axis represents the power generation by the plant. So of course, 0 means nighttime or 0 power. 1 means nameplate power, so close to 1.8 megawatt. So you can clearly see the dots trend that once the plant start generating around 50% of the nameplate, so 900 kW, 1 megawatt, more and more dots starts exceeding the NC limit of 105%. So this is a typical behavior of a plant whenever a plant or a group of DR starts backfeeding a section of the feeder or line, it starts pushing the voltage high. As long as the net consumption, of course, it will be low, but it starts net generation and backfeeding, the voltage goes up. So this is an example of 1.8 megawatt in a rural agricultural farm. So of course, not much load there, and was pushing the voltage high. So in that particular case, that utility has the agreement that if needed, they can ask for the plant owner to change the power factor. And after changing the power factor in the absorbing direction, there was an error in the middle. We are not showing that figure. There was the technician went to the site rather than absorbing VAR, it accidentally selected the VAR in the injection direction. So again, the plus minus confusion. So there are a couple of a period where the plant was actually injecting VAR and pushing the voltage further high. You can expect it's already high and now you're pushing VAR, so it was pushing the VAR further high. Anyway, after recognizing the problem, they went back and fixed the power factor, I think around 0.97 absorbing, After that, you can see the January 13 when he just plotted the data for the month. Almost there is no point, even when the plant was generating 0.9, 0.95. So there was almost no point where it was crossing the 105 limit. So I typically like to show these results just to show that how simply fixing a power factor can solve the voltage problem at a localized level of one particular plant, one particular location. If the plant is causing the voltage problem, by absorbing VAR to a power factor, it can fix that problem. But of course, there are other discussions there. We'll get into that later. So this is an example from the field, largest scale plant solving their voltage problem, at least the localized voltage problem, by changing the power factor to the absorbing limit. Then I'm showing a couple of examples from our laboratory testing. So the picture that you are seeing on the left is a section of our smart inverter test lab in Knoxville, Tennessee office. Some of you may have visited that if you have joined any of our smart inverter workshop before. So right now, this is a kind of a 3 inverter connected in a residential fashion. There are 3 of them connected to a medium volt, a 50 kVA transformer with a defined length. So basically, they are seeing different types of voltage at their terminal. Of course, there are 3 different inverters. You can see clearly 3 different brands. So what I'm showing here is a summary from one example from this report. Of course, you can also download the report if you want to see more detailed results. I'm just showing a comparison of if I let all these inverters run at unity power factor, like what will happen to the voltage at the 3 houses when from no generation, each inverter starts generating power. So you can see first house C, we turn them on, then we turn house B, then we turn house C. So gradually each house starts generating power, voltage is pushing high and high and high. And it's not just their own house, the neighbors' power generation also pushes their voltage because of the transformer secondary is pushing, going up. So that's what you're seeing here, and you can follow the trend depending on test scenario, what is the voltage looks like. But ultimate point is that if we let them unity power factor, when all 3 inverters start generating, the voltage can go up a couple of voltages. Of course, that will depend on the size, wire size, length, a lot of factors. But main point is, before solar generation, voltage was 240. After they start generating, voltage can go to 244, 245, 246, depending on the impedance. However, if we run all these 3 inverters into 0.9 power factor mode, which is a little bit extreme, typically 0.95, 97, those are used. But just for the demonstration purpose, if we run them at 0.9, for the same power generation, you can see that voltage did not exceed more than 2 volt or 1.5 volt here for the house C. So this is an example to show that especially this reactive power control, power factor control can have significant impact, at least on the low side of the medium voltage. We'll show more examples on the medium voltage later, but this is where you're seeing 240 volt side. Clearly, if the house metering point, the voltage can be significantly impacted by solar generation and also by having some reactive power absorption by the inverter. You can reduce the voltage increase. So this is a residential example. Previously, I showed the larger scale, megawatt scale example. One more result from this analysis or this test. These are test results. These are not simulation again. These are laboratory test results. So here I'm showing only the transformer secondary voltage here, the low side voltage of the service transformer, and 4 different power factors. So one means all 3 inverters running at unity power factor. The green one means when all 3 running at 0.95, that's how these figures are. And of course, the power generation is same. Gradually, all of them are generating. So you can see that unity power factor is as high as like 243.5, then 0.95 is keeping it low, 0.9 is keeping it further low. If you go even more aggressive, 0.85, it can even push lower. So this is to show that by having a power factor control or reactive power control, can effectively control this transformer secondary voltage, which is not only impacting the customer with solar, it also impacts customer without solar. So if solar pushes the secondary voltage, all the customer connected to that transformer will see high voltage. So those type of situation, having this reactive power control by a simple power factor function can effectively reduce the voltage increase. Any question? Okay, these are simple, so let's move on. Next, I'll show two example scenario. Pay attention to the top in this header where I highlighted the part, the P max equal to S max. So what I'm referring to here is the excuse me, inverter design question. The point I'm highlighting here, the inverter, getting some background noise, Amy, if you can find. The inverter being a power electronics is always a VA limit, volt ampere limit. I think I mentioned that in the previous day. Because of the thermal limit, because of the switching devices, they are always limited by volt and ampere. So it can never operate outside this circle. Now, if circle is S, if that maximum value is S max, and maximum power is this line that further it can go, which is P max, if these two are same. So for example, an inverter is designed for 100 kVA, and the manufacturer is also selling it as a 100 kilowatt inverter. VA is the limit, design limit. Kilowatt can be adjusted by software, but it's a manufacturer choice. They can say that, okay, I designed it for 100 kVA, I'll also sell it for 100 kilowatt. So that's the example I'm showing it here. In that case, if there is no reactive power requirement like this one, 0 power requirement, then of course the inverter can generate 100 kilowatt when the sun is available, and perfectly okay. In that condition, that when the inverter is generating its maximum power, if you ask the inverter, if you ask the inverter to operate a non-unity power factor mode, previously it was operating at unity power factor mode, no problem, because there is no reactive power demand. Entire VA was used to generate the kilowatt. At that point, if a DARMS or DMS send a command that, okay, operate at 0.97, in that case, if it has to obey the command, then it has to generate a reactive power and move the operating line to a position like this. And you can clearly see that in this case, to generate this Q, to operate at that power factor line, it has to reduce the power. So this is the point I wanted to highlight here. Whether it has to reduce or not, it depends on a lot of things. First of all, is this P max and S max same? If that's the case, question is, do I have enough DC power to generate the maximum power? If that's also true, then the example is that what I'm showing here, that yes, I was generating the maximum power when power factor was unity. The moment I receive a command to go to a non-unity power factor, I have to reduce power to generate that Q to maintain that power factor. If I send a further command, so initially was 0.97, now command came 0.92, then it has to go even further lower. So real power has to go further down. So this is an example that by having a power factor function or having a more aggressive power factor function can impact the active power generation. So this is something might be important. You may already faced it, that plant owners or system owners or vendors may ask the question, okay, to do that I'll incur revenue loss. So what is that? This question may come. So the source of this question is how the inverter is being designed and how aggressively the volt bar is being used, or so power factor setting is being used, and also where it's located. And if you remember day one, our first session, we showed that if you're in California, in Arizona, a lot of days you have bright sunny days. So a lot of potential to generate or operate at full power versus if you're in Florida, North Massachusetts, you have a lot of cloudy conditions where you may never reach to the full power. So that also depends, that if you're operating here already, and of course you can operate in this mode without any curtailment. So curtailment question comes only when you have the potential to generate full power or high power, and then because of power factor setting, you have to reduce it. So one of the fundamental question is how the inverter is being designed. So that's number one. And I'm giving another example. It's just the opposite direction. Now look at this scenario where I'm saying that this is a 100 kVA inverter, but maybe manufacturer is selling it as a 90 kilowatt inverter. So 90 kilowatt, 100 kVA. So P max is slightly less than S max, or the other way. S is slightly higher than P. If that's the scenario, what happens? So again, same example. This is a 100 kVA, but the inverter is rated for 90 kilowatts, so it's generating 90 kilowatt at unity power factor. So at that time, the same command comes that go to 0.97 power factor. So it will happen like this. So it will go to that power factor and it can generate that Q without reducing the real power because it's within the circle. So that it doesn't have to sacrifice active power to generate that. Now, if next command comes, go further higher, say 0.95, maybe it will be able to go there also because now it's still within the circle or on top of the circle. So it will be able to do that without reducing the power. If the setting goes further high, say 0.95, 0.9 or 0.85, yes, now it has to curtail power. So this is what I was referring to, that using a too aggressive power factor may help you with the voltage, but the consequence is, one consequence is that more active power generation loss. And later I'll show that that also means that the plant will absorb a lot of reactive power. So where that reactive power will come from? So that will be another question. So again, so these two slides I'm just trying to highlight the importance of inverter design, how the manufacturer designed or put the rating of the inverter. If P and S max are same, potentially there will be more energy loss due to reactive power support. If the S is slightly higher, and again it's not linear, so if it's slightly higher, say 100 kilowatt, 110 kVA, then almost 44% of the bar can be generated without sacrificing active power. So that's kind of the comparison or compromise. Any question? Okay. If not, next 2-3 slides, I'll show you a couple of examples from the field. This is again a 1 megawatt PV plant, I think in Massachusetts. You are seeing a couple of things here. The top left figure is actually showing the PV plant's power factor for the whole day, actually 2 days. The blue one is when the baseline, which is basically unity power factor operation. And you can see that pretty much other than the early morning and end of the day, the plant maintained the unity power factor the whole day. The test day, when we asked the inverter to operate at 0.98 power factor, similar thing, other than the early morning and end of the day, evening, it pretty much maintained the 0.9 power factor for the whole day. Corresponding, if you see into the active and reactive power, so you can clearly see the top one and the green and blue are representing the power. Slight changes, slight reduction in the active power, maybe some locations. And also, in real world, having 2 days exactly same is very difficult. So this is as close as possible. But the main thing that you can see from the reactive power side, baseline day when it was a unity power factor, the plant almost whole day did not absorb any reactive energy. It was flat except something happened in the evening, late in the evening. But on the other hand, when it is a 0.98, you can clearly see that it is almost linear to the active power. Power goes up, reactive power goes up, power becomes flat, saturated, reactive power also becomes flat, and then comes back when the power goes down. So power factor is simply, in power factor mode, reactive power is proportional to the active power. And 0.98, 0.95 depends on the ratio, but it's linearly, almost linearly related. So that's what you are seeing, that doesn't matter what's the voltage, when the real power goes up, reactive power will go up and follow that trend. And this is the amount of reactive power that the plant will be absorbing on that day. As a distribution operator or transmission operator, of course, your question will be, if I have hundreds of them or thousands of them in a substation all absorbing, where the reactive power will come from. So that's why it's also important that, yes, more aggressive power factor may help with the voltage more, but the opposite side, from customer side, impact on the energy production, from utility side, you have to provide that reactive power from somewhere. And on the other right side, I'm showing, this might be the answer to the second chat question. We have seen multiple times, different locations, different vendors, different models, that typically inverters do a very decent job to maintain the target power factor once its power generation is above 20% of its nameplate. So this is a percentage of nameplate here. So you can clearly see that above, once this power generation is above 20%, it's pretty closely maintained the power factor of target power factor. Below that, and this is, again, this is consistently we have seen it, below 20%, it typically struggles to maintain the power factor. And you can imagine that this is a very simple reason. When you are at low power, any small error in the measurement of Q, any error in the control that maintaining the target power factor or calculating the based on P how much Q I need. So if it makes any error in the power calculation, that will impact the reactive power calculation and also generating that reactive power. So all these errors are magnified because you are dividing it by a small number, 5%, 10% power generation. So basically error gets magnified. So that's why, that is the main reason that inverters typically struggles to maintain the tight power factor accuracy when the power generation is low values. So I'm not sure this answers your question, but if not, please feel free to chime in with additional question or comment. So I'm reading the chat questions or comment, the third one. We are seeing proposals for fixed capacitors, say 12 MW, as part of large projects, say 150 megawatt. Will they only use these at times when the PMAX cannot be assured without supplemental VAR support? I heard this one, that transmission connected plant offered that. Without knowing a little bit details that how they are controlling the capacitor, that would be a good question. That is it always on, or is it like actively managed based on what the plant is doing? Those will be the question. And also, capacitor may indicate that it is a low voltage scenario, whether they are trying to fix that low voltage by having a fixed capacitor. I also heard the term the smart capacitor, which is basically turn on, turn off, depending on either voltage or VAR demand. So maybe you need a little bit more information that what is the purpose or how they're controlling the capacitor, if you know that information. Another question, as one can see on slide 20, the slide that is showing right now, the reactive power is non-zero while maintaining unity power factor. How close to zero is close enough? That's a good question. When you ask it to operate unity power factor, we have seen power factor like 0.997, 998. Occasionally, it can go up and down, and that depends on a lot of cases. It depends on their islanding detection mechanism. That some inverter or one of the islanding detection mechanism is to push a reactive power to see whether you can push the voltage or not. So if an inverter use that mechanism of islanding detection, then you may see that with certain time interval, VAR goes up and then comes back, maybe zero or opposite direction, then again goes up and down. So oscillating behavior, but you will not see a sustained high Q or high low. So pretty much we have seen 0.99 and then a third digit of power factor maintained by the inverters. If you ask it to operate at unity power factor, except whenever, if the inverter is using a reactive power based islanding detection mechanism, then you may see some oscillatory behavior across zero line. Okay, any other question or comment? If not, let's move to maybe maybe one or two more examples. The same example, again, I'm showing the same but a little bit different way, 0.98 absorbing. So one thing that I wanted to highlight is the left figure here. You are seeing the voltage in three different locations. Same plant, same test result. What we are showing the left side is the voltage measured at three different points. The top one is the voltage at PV plant, low voltage side. By low voltage side, we are referring to the low voltage side of the interconnection transformer, typically 480 volt or some 400 volt or 600 volt. and sometimes non-standard voltages are possible also low side. But basically low side of the transformer. The middle one is showing the high side of the transformer. Basically, that is the medium voltage. As utility, that's what you are interested, what happened on the medium voltage side. And the third one is at the substation. So we had meters both at the low side and high side of the transformer at the plant, a megawatt scale plant, and also what happens to the substation, maybe first pole outside the substation, the voltage measurement. And this is 1 megawatt plant, not a very large one, and it is relatively close to the substation. So those are also factored in when you explain the voltage. So what you are seeing here is the blue one is the unity power factor operation there. Like basically we call it baseline there. And you can see the voltage is quite widely spread as a whole day. So widely spread, and the median is somewhere around 1.043 for the low voltage side. When you activated the power factor, it kind of tightened the voltage. So it was maintaining, increasing or decreasing the reactive power. And effectively that was reducing the voltage variability. That's why you see a little bit tighter voltage. And you can also see the median has shifted towards the left, and 0.98 is absorbing. So it was keeping the voltage low relative to the unity power factor there. So that we have consistently see this behavior, especially on the low side of any DR plant. Reactive power managed to keep the voltage low. Whether same effect can happen on the medium voltage side after you go through the transformer and the other customer around it, how they behave. This particular case, you can clearly see now that's not the case. This medium voltage side, yeah, it tightened the voltage, but it does kind of look like opposite direction. Rather than voltage lowering, it's kind of looks like it's still on the high side. So that main reason is that it's 2 different days. So the other day maybe totally load was changed or different type of load condition was there. So that's why in real field, very difficult unless you do long-term analysis that what is the direct impact of that, or do immediately 5 minutes before, 5 minutes after. So these are the kind of 2 different days, that's why it didn't match. And also medium voltage side, the impact is not that much until it's a large plant or it's a weak point on the circuit, low XOR ratio, or sorry, high XOR ratio point. Similarly, substation is very difficult to move any substation voltage because you have regulators and other things to maintaining the voltage. So most cases, we see the behavior impact, direct impact on the low side. Depending on the size and penetration, may also see some impact on the high side. Maybe we have some examples later. And then substation is very difficult. By having a small distributed connected PV can move the substation voltage. The other point I wanted to highlight here is that what happened to the net reactive power demand at the substation, and this is what is shown in the right side in the middle figure. This type of data is also only possible if you have the meters available to collect the information. So you can see that the unity power factor there, the power, reactive power was relatively close to 0 for most of the days. But when the unity power factor there, the plant start absorbing VAR, and you can see in the middle of the day, pretty much for the several hours, the reactive power was constant around maybe 200 kVAR, and that's the amount you can see the VAR was reduced, or maybe transmission was injecting the VAR, supplying the VAR that is being absorbed by the plant, that amount. Something happened in the middle of the day, capacitor bank, most likely because we didn't see any cap operation. So that indicates it's a capacitor bank switching this large, almost 600 kVAR step capacitor on and off. And voltage, very difficult to adjust in the plant and substation. High voltage side difficult because you have a lot of cap operation, cap bank switching. So unless those are all coordinated, it is difficult to say which one is impacting what. And typically, cap operation, cap bank switching has larger impact on the voltage relative to a small 500 kW or 1 megawatt plant. Unless the plant is 5 megawatt or 10 megawatt, typically capacitors and regulators have more impact on the voltage than the Q injection of 200, 300, 400 kVAR from a megawatt scale plant. So those are the examples are shown here. Looks like there are a couple of questions. What's the location of the operating cap bank? So that I don't have the information right now. It's in the circuit model. The cap banks are shown there. It's somewhere between the substation and the plant, if I'm not mistaken. We have that information, but not in this slide deck. There's another question. Assume the system angle changes at the point of interconnection due to a plant line outage. What impact does the phase angle change have on inverter? Okay, I'm not clear about the question. If it's a normal operating condition, it's a line outage. Is it a single line outage, or is all three-phase outage, or is it a momentary or permanent? There are a lot of factors there. Unless Michael will chime in and explain further, I would say, of course, the inverter tries to maintain the synchronization of the grid, and phase angle will dictate the real power injection, as we discussed yesterday. So, yes, single line outage for a couple days. Okay. So, single phase outage, if you remember the islanding discussion that we had, resultant of the single phase outage, what the inverter will see, like at its terminal, whether it will see an outage or it will see 3 good voltages within the operating range, that will dictate. So if the inverter sees the outage or a protection relay pick up that open phase, of course it should disconnect. But if it fails to detect that, then there is a possibility that it will keep on operating at some higher voltage on the other 2 phases. And as long as there are load, it will inject current to the system. It will sustain a couple of days. I think we heard that example, that it stayed connected until a utility noticed that. So, yeah, there is a possibility that if your outage is somewhere not immediately at the terminal of the plant, somewhere upstream, and you have load between the outage phase and the plant has certain type of transformer configuration, and there is a load present, then inverter may not see a abnormal voltage and keep operating. That we call single phasing, and I believe most utilities for larger scale plant, either the DR has to demonstrate that it can detect it, or it has to put some negative sequence relays to detect that and shut down the plant. And within our group in 174B, we have developed a method, and so far we have done the simulation-based demonstration that the inverter, using its own negative sequence component, can also detect, most cases, the feeder level open phase condition. So far it's a simulation-based proof of concept. Next year we want to do some hardware level verification of that proposed method. And yes, this is not island, this is a single phasing event. And we had the example that plant can keep operating longer time, whether hours or days, that may depend. But if everything lines up, that it can continue to operate because it will not see the abnormal voltage. Okay. So this is another example. I'll not go through the details, only make 2 main points. In this case, we ask the plant to operate 0.93, which is more aggressive compared to 0.98. And you can clearly see that the amount of reactive power absorbed has gone up. Previous example, it was around 200 kVAR. And this case is almost 350 kVAR was the main, almost the whole day the plant was absorbing. Of course, it will help the voltage, reduce the voltage, but the more reactive power will be absorbed. And power factor, you can see the similar behavior, that above 20%, it maintained 0.93. Below that, it struggled. Okay, and if you compare the reactive energy absorbed, 0.98, it was 1.76 megawatt hour, and this day 0.93, it was almost 2.78. So you can clearly see that more and more reactive power energy will be absorbed if you go more aggressive power factor setting, and that has to come from somewhere. So this is the end of power factor. Again, very simple function being used for several years. especially for single plant causing overvoltage, can solve that problem easily. When you have multiple plants in a feeder, overvoltage in different locations, coordination might be challenging to use power factor. And sometimes also it mentioned that power factor is very good if the voltage problem is caused by the plant. Plant is causing the overvoltage by backfeeding or power injection, then relatively proportionate reactive power will solve that problem. So when next topic is the volt var, which is more like you are responding to the voltage, may or may not be caused by the plant. Maybe overvoltage is already there or something else. So that's kind of the volt var. We'll discuss that. If you're not familiar with this volt var function, I'll spend maybe 1 minute or 2 minutes to explain that. Just to very basic, what is actually volt var function means. So if you look into this graph, y-axis is the reactive power. So top side we are showing injection, bottom we are referring to absorption by the plant. So here plant is injecting, here plant is absorbing. And of course x-axis is the voltage. Voltage at the terminal of the inverter, which inverter always monitor, or a point where as utility you want the plant to respond to a voltage at certain location. So whatever voltage you want the plant to respond to that has to be the reference voltage feedback to the controller. So in this wave shape, there could be a lot of shape possible, but the common one people discuss that you will have a target voltage, say nominal voltage, 1 pu. Or you have a severe program where you want to maintain 0.98 voltage. So whatever your target voltage, that should be your VREF. Now across the VREF, there might be a plus minus 1%, plus minus 2%, plus minus 3% voltage. You don't mind if the voltage varies. Yeah, you say normally voltage always varies to 3%, so I don't care. So you specify a range where you say, voltage variation is fine, I don't need any reactive power support. That is known as deadband. And typically, V2 and V3 refers to the edge of the deadband. So VREF is the center point, you can assume. V2 is the lower end of the deadband. V3 is the upper end of the load band, deadband. Right now it's shown as a symmetric, but that doesn't mean that it has to be symmetric. It could be one end 0. Say V2 is same as VREF, and other end is the V3. That's also possible. Deadband can be 0 also possible. So this is just a generic. By defining V2 and V3, you can change the shape of the deadband. Similarly, Q2, Q3, typically expectation is that reactive power in the deadband will be 0. But if any utility wants that I want a certain watt to be absorbed or inject, even when the voltage is within deadband, so then Q2, Q3 can be also adjusted with the non-zero values. But I'm showing the most common way people use volt var function. Then what happens that if the voltage goes below V2, which will be considered as a low voltage condition, you expect the DR plant to inject VAR to help boost the voltage. Below V2 is a low voltage, say 0.96, 0.95. You want the plant to inject VAR to boost the voltage. So that's what this curve will represent. Voltage further goes low, plant tries to increase VAR. At certain points, say V1, it will inject the maximum VAR it can inject. So it will hit its limit. And above that, it has no room to increase VAR anymore. So that is what is typically represented by this flat line. That at V1 voltage, I reach to my limit based on this curve or based on my capacity. After that, if the voltage goes further low, I'll just maintain that reactive power, but will not change. On the other hand, if the voltage goes above V3 here, this will be considered as high voltage condition, and the expectation will be the plant will start absorbing VAR to pull the voltage down and follow this curve. So that is what I mean by curve, that it is a relationship at what voltage, how much VAR the plant should or inverter should absorb. So this relationship. Same thing at V4, it will reach to its maximum limit of absorption. After that, if the voltage goes high, it will maintain that reactive power, but it will not be able to increase it any further because it already hits the limit. So that's how the volt var function is defined. You can clearly see these 4 points, and this VREF defines the shape of the volt var curve. Mostly these four points. By adjusting V1, V2, Q1, Q2, you can change the slope here. like the droop curve, you can change it. Similarly, V3Q3 and V4Q4 will dictate the slope. You can make it more aggressive or less aggressive by pushing it left or right. Similarly, you can change the magnitude of the var by changing the Q1. You can go here, you can define it here, so you can decide how much var you need, of course, within the capacity of the plant, similarly on the other side. So there are a lot of flexibility in the definition of the Volvar curve, and by using a pair of points, it's easy to configure those definition. Now, what do we mean by autonomous? As a utility, you have to first activate or say that Volvar function has to be activated, then has to have a profile like this, that relationship or Volvar characteristics. Once that is configured and activated, then if there's any change in the voltage, for example, voltage moved from Vref to V3, which is still within the dead band, there is no change in the Q. So inverter saw that voltage moved, but also saw that the voltage is still within the dead band, so did not change the reactive power. After that, if the reactive power voltage change, like voltage has moved from here to this point, and it then said correspondingly, it needs to generate this much of var, and that's what the plant will do or inverter will do. As long as voltage is here, it will absorb this much of var, and result of that voltage may come back and settle down at operating point. So if the voltage goes further low, reactive power will go back. So this operation is autonomous. If voltage change, reactive power will change following this curve. So that part is autonomous, but activating the function, selecting these settings or configure characteristics curve, that has to be done by somebody. Okay, so if the voltage go further high, there will be no change in the reactive power because it's already in the maximum absorption limit. So that's what it means here. Now, if it goes other direction, you can see clearly the reactive power is moving. If it goes low, reactive power will go into the injection mode. And if it goes further high, it will go further high. So this is another important difference in the Volvar function. If it's configured the way it is shown right now, and for whatever reason, the grid voltage change from high voltage side to low voltage, maybe feeder reconfiguration, sudden load change, or some operation, the plant will automatically change the direction of reactive power from injection or absorption for high voltage. It will go to the injection for low voltage, as long as it is defined like the way Volvar function is shown here right now, or depending on your voltage. If you compare that with power factor function, once you configure it for absorbing mode, it will always absorb var proportionate to the real power until somebody changes the direction to the injection mode. So power factor function is always either positive or negative or absorption or injection, and is proportionate to the power, not directly related to the voltage. So if any reason voltage was expected to be high, that's why it was configured to absorb var, voltage goes low, it will still absorb var and will pull the voltage further down. So that's another difference, and I'll summarize that later. Power factor function is proportionate to active power, no direct relation with the voltage. On the other hand, Volvar is proportionate to the voltage, but no direct relation with the power. Of course, there's indirect relation, but no direct one. Okay, any question on the Volvar basic definition? Again, those are all flexible points, and the standard defines that how far you can adjust them, and we'll discuss that in the afternoon session. So next, there's a question, what are the typical value for upper and lower limit for V1 and V4? There is no typical. Question is which standard you want to follow. Like if you go to the IEEE 1547 2018, I have to go and check and maybe have it in the afternoon session. This age is 0.98 and 1.02, so dead band is plus minus 2%. This one most probably goes 0.9 or even lower. So that tells you that how you want to define this slope, that how aggressive or benign you want to make this slope. And it will continue that. And slope can go, you can define it, say 0.8, just to reduce this slope. But another thing we have to remember, in the standard, from 88% to 110% is defined as the normal operating condition. Below 80%, above 110% are defined as abnormal voltage condition. And there are totally different requirements that how the DAR should behave during the abnormal voltage condition. These are the functions. Okay, I'm hearing echo. So these are the functions defined for normal operating condition. So voltage might be 0.8. That doesn't mean that it will continue to operate till 0.8. It will be just dictate that at the age of